Let G be the set of all 2 cross 2 non-singular real matrices. Prove that G is a group under the usual multiplication of matrices. Now coming towards its solution, non-singular matrices are the matrices whose determinant is not equal to 0. Since it is a general proof, so we cannot construct Cayley's table, so we will solve it generally. To prove that G is a group under the usual multiplication of matrices, we have to satisfy all the 4 axioms of matrices. First axiom is closure law. Let A, B belong to G. Since A and B belong to G, it means that A and B are non-singular matrices of order 2. Since all the members of G are 2 cross 2 non-singular matrices. So, since the product of 2 non-singular matrices is a non-singular matrix, then the product of A and B is also a non-singular matrix of order 2, which implies that AB matrix belong to G. For all A, B belong to G, so closure law with respect to multiplication holds, which means that first axiom of group is satisfied. Second axiom is associative law. Associative law in general holds for 2 cross 2 non-singular real matrices. So if we take any 3 matrices from G, then A, B into C is equal to A into B, C for all A, B, C belong to G, which implies that associative law with respect to multiplication holds in G. So second axiom of group is also satisfied. Third axiom is the existence of identity element. I is equal to 1, 0, 0, 1 is a non-singular matrix of order 2 and it is given that G is the set of all 2 cross 2 non-singular real matrices, which implies that I also belong to G. We know that I is an identity matrix, hence I is an identity element of G with respect to multiplication. As the existence of identity element has been proven, which means that third axiom of group is also satisfied. Fourth axiom is the existence of inverse. Let A belong to G, which implies that A is a non-singular matrix of order 2 since all the elements of G are non-singular matrices of order 2 and inverse of each non-singular matrix exists, which implies that inverse of A, that is A inverse, exists, and inverse of A is also a non-singular matrix of order 2, so which implies that A inverse belongs to G. Since the existence of inverses has also been proven, which means that the fourth axiom of the group is also satisfied. Thus, G is a group under the usual multiplication of matrices.